Hello, everyone, and welcome to tonight's session on elimination reactions. Today is part 2 for substitution elimination. We did part 1 recently on SN1 and SN2, and today we're going to complete the basics before we jump into the upcoming session on how to distinguish between them, which is probably the session you're all waiting for. So let's start with some quick introductions. Let me know in the comments what brings you here today. Are you here for an Organic Chemistry 1 class? Are you preparing for an exam like the MCAT, the PCAT, the GAMSAT, the DAT, or anything like that? Let me know in the comments. Also, let me know where you're tuning in from. Hold on, that just changed on me. Make sure I have everything all set here. Let me know if you can hear me. Make sure the audio is working, and then we'll go ahead. Med Brit is an Orga 1. C is an Orga 1. Kempsey, good evening to you as well. Nevi, let me know how to say your name, is an Orga 1 from Seattle. Damaris, Orga 1. Cooper, Orga 1. Kempsey, excellent. Kaylee, Orga 1. Rogaya, hope I said that somewhat correct. Yes, can hear me. Excellent. Aaliyah, it is good to see you as well. So let's jump in with a quick overview. Let's start with basics like so. I'm from South Africa, 1400. We're writing an exam, so this is good timing. Sid from California, Pinchik from India, Barbados. I love it. There are students here from everywhere. Back when I used to work with students in person, I was limited to anywhere that I can drive within half an hour or so. And now we have people from all over the world. This is absolutely amazing. So let's go ahead and jump right in. Here we go. Before we go into the nitty-gritty of the reactions, let's do a quick overview for the E1 reaction. If I start with a molecule like this, a simple carbon chain with bromine, and I reacted in the following conditions: H2SO4 in H2O, add some heat to catalyze the reaction, the product is going to have a pi bond right there, like that. If I take, so let's do that. If I take this reaction, and the only thing that I change here is instead of H2SO4, I'm going to swap it out and use NaOH. Now I have the E2 reaction. So what's the difference between them? If I have the same starting molecule and the same product, where swapping the reagent changes the name of the reaction, but nothing really appears to have changed, this is where memorization will absolutely fail you. I want you to instead approach this from understanding. I want you to understand what is happening with each reaction, why it's happening, what the reagent is going to do, why the reagent is going to do that, instead of just straight up memorization. So if you're with me and you agree to take what you learned today to help you understand rather than memorize, let me see a couple of hearts in the comments, and we'll go ahead and start with the mechanisms. We'll break it down so that you can actually understand, so that the reactions themselves make sense. I do see the hearts coming in. Excellent. For a copy of today's session notes, everything that I'm writing here, along with my brand new substitution elimination midterm worksheet that's not available on my website, go ahead and put worksheet in the comments and I will send you the link. We'll start from the beginning with the E1 reaction. What does the E and what does the 1 actually stand for? What we don't have in the abbreviation here, if you think back to SN1, the S and the N and the 1 all stood for something. Here we only have the letter E. It should really be BE1 reaction because this is a beta. We don't have an abbreviation for that. The E stands for elimination. And the 1 does not tell us that it is one step. Instead, it tells us that it is unimolecular, which is really, really important. That 1 right here simply tells us that it's one step at a time in what will ultimately be a multi-step reaction. What exactly is happening here? With a beta elimination, we're looking at a carbon that is beta to, well, what are we actually looking at? Let's draw out the molecule instead of speaking in hypotheticals. When looking at substitution and elimination, there is the carbon that holds the leaving group. In the previous example, I showed you a bromine. This is considered the alpha carbon. The alpha carbon, that's the ground zero. That's where the attention is focused. And any carbon next to that alpha carbon, that is considered the beta carbon. So in this case, I have a beta on the right and I have a beta on the left because any carbon next to the alpha, doesn't matter how many you have, 0, 1, 2, or 3. Well, 0 wouldn't be a beta, but 1 or 2 or 3, they would all be considered the beta carbon. And when we're looking at elimination, specifically, we're looking at the hydrogens that are sitting on that beta carbon. So in beta elimination, we're specifically going to remove 2 things: the alpha leaving group and the beta hydrogen. And in its place, we're going to have a pi bond. So the pi bond is going to form where everything left. So let's, well, actually, before we go into the mechanism, we need one more thing. What does that elimination, what kind of molecule do you know that likes to grab hydrogen atoms? Well, a base is something that, depending on which definition you look at, you have the Arrhenius base, grabs an H plus in an aqueous solution. You have the Bronsted-Lowry base, which is just going to grab an H plus off whatever, or use its lone pairs to attack something that attack that H plus. And then the Lewis definition doesn't really apply here, but we're looking at the lone pairs. I just gave you 3 different definitions where I talked about something grabbing an H plus, which is positive, or using its electrons, which are negative electrons grabbing an H plus. That base is something that is negative or partially negative. And that's the key we're going to look at in this reaction. So we have all the pieces. Let's redraw this molecule a little bit less marked up. We'll put bromine back as the leaving group, and we'll bring back the reaction conditions, which I gave you earlier, as H2SO, or let's keep the colors set different so that you can follow where everything goes. H2SO4, H2O, and heat. The first step in the reaction is the base grabbing a hydrogen, but I didn't actually give you a base here. I gave you H2SO4 and H2O and heat. So what is going to act as the base in this situation? Well, first of all, H2SO4, not our base. It's a source of proton donors in solution. It's an acid catalyst. And yes, you will have the HSO4 minus, I did that very wonky. HSO4 minus is technically the conjugate base, but we are not going to use it because this right here is not strong enough to abstract the hydrogen. And so if your professor shows this to you, just tell your professor, Leah said you're wrong, but maybe use nicer words than that. If we don't have a base given and you only see an acid catalyst and a solution, the solution itself is going to act as your base. This is called a solvolysis reaction. Solvolysis, the solvent is going to do the reaction here. And the solvent, water, is a weak base that we're going to use for this reaction. The first step, though, is nothing to do with the base and everything to do with the fact that bromine Let's make this a faster reaction. So I'm going to make it more substituted, and I'll talk about this soon when we compare and contrast. In a situation like this, I have bromine, which is a highly electronegative atom. And even though it's covalently bound to carbon, even though it seems to be happy, bromine is greedy. And it starts to pull and yank on that bond between carbon and itself because it wants the electronegativity more around itself until eventually it pulls so hard and completely breaks off. This is how the reaction begins, where we have the carbocation intermediate forms, and somewhere off in solution, we have a Br minus, happy, stable, despite having a negative charge, surrounded by water, never to be heard from again. And so something else is potentially going to attack. In this case, we said we have a solvolysis situation where the water is acting as the base. And yes, water, H2O, is a polar protic solvent. This is very helpful for an E1 reaction because the polar protic solvent is going to surround all the charges. The partially negative oxygen on water will stabilize the carbocation. The partially positive hydrogens on water will stabilize that Br minus. It's very ideal for a situation, for a reaction that has a lot of charges. So yes, on the polar protic solvent. Now, one of these water molecules that happens to be hanging around near the fully positive, near the carbocation, is going to potentially interact at the carbocation, which is an SN1 reaction we covered before, or in this case, it will act as a base and grab a proton. So we looked at the concept of the beta carbon earlier, the carbon that is next to the alpha, and we talked about how it's the beta hydrogens we're looking for. So we'll put the light green beta hydrogens at this position and the light blue beta hydrogens, oh, we don't want them the same color as the water, so I'll put them in pink at this position. I'll show you the mechanism where we grab the light green hydrogen. And the reason, let me back up. The reason we can grab that hydrogen is given that the carbocation is right here. The carbon, even though it's stabilized being a tertiary carbocation, it doesn't really want that positive charge. And so it starts to pull and pull and pull on electron density from all the atoms around it. And as it pulls on the electron density from here, pulls some from the hydrogen, it gets pulled away. These hydrogens are now going to be very partially positive, and that is why the base is attracted to them. And the base is attracted to the point where it's going to reach out, attack, grab that hydrogen, and break the bond, where instead of collapsing onto carbon, it's going to collapse in the direction of that positive charge. The electrons go where the positive is pulling from, and that gives me the final product that looks like this. My carbon skeleton as I see it, but now with a pi bond sitting between where that hydrogen was grabbed from and where the carbocation used to be. In other words, the pi bond sits between the alpha and the beta carbon. This is the final product for the E1 reaction. But I have a question for you. What if I have a water molecule that instead chooses to grab the pink hydrogen instead of the green one and collapse the pi bond, collapse the electrons in the direction of the carbocation to give me a different pi bond? Is this considered wrong if I did the same exact mechanism and just happened to grab a different hydrogen to give me a different type of pi bond? Once again, you'll notice that the pi bond here is between the former alpha and the beta. Very good question, M. E1 is always Zaitsev. It's not an always situation, but instead it's a major minor situation. So let's take a step back and talk about what we're looking at here from a stability perspective, and then we can come back and see why we would choose one over the other. When it comes to pi bond stability, just like we saw with carbocation stability, a pi bond is going to be more stable the more substituted it is. So if I have a pi bond that looks like this, just 2 carbons double bound to each other, this is not substituted at all whatsoever. And this is not very stable. It is still going to form. You'll see this in different reactions. Well, you'll probably see an alkyne version of it more in your reactions, but you'll see this as well. If I take a molecule, though, and I put the pi bond, but now I have that one substituent coming out of it, this is monosubstituted. And the best way to tell is to use what I like to call the highlighter trick. You highlight the pi bond, and then you count how many arrows you can draw from the pi bond that you highlighted to a nearby carbon. In this case, 1 is how I get mono. If I take this pi bond and I draw 2 substituents out of it, or I take this pi bond, let's do it like this. I take the pi bond and I draw 2 substituents. I take the pi bond and I draw 2 substituents, or I take the pi bond and draw 2 substituents. Let's show each one with the highlighter trick. Highlight the pi bond. How many arrows to carbon? 2, 2, and 2. These are each considered di-substituted, but they're not the same stability. What you're looking for with a di-substituted pi bond is, even though you have 2 substituents, where they're located matters. If they are close together, they are butting heads, they're in each other's spaces, that makes the molecule less stable. But if they are far, far away, they're not in each other's spaces, they're now more stable, more comfortable, lower energy, making this the most stable of the di-substituted and this the least stable. So what I'm doing here is I'm drawing the least stable at the top, and then the arrow is in the direction of increased stability. So the lower down we go on this chart, the more stable. That makes this di-substituted least stable of the di-substituted, and this one the most stable. If I continue this trend and I draw a pi bond with 3 substituents, let's prove it with the highlighter trick. Highlight the pi bond. 1, 2, 3. This is tri-substituted. And then, last but not least, I draw the pi bond with 4 substituents. Let's prove it with the highlighter trick. And I have 1, 2, 3, 4. This is tetra-substituted. And this one here is the most stable. Let me know in the comments if you memorized the concept of Zaitsev's rule and you're ready to understand it now from a logical perspective. If we are looking at many, many different pi bond options, where the lower down we go on this table, the more stable it is. If we then look back at the reaction here, just comparing the stability of the pi bonds, let's use the highlighter trick. I have this right here and this right here. The one on the left has only 1, 2 substituents. The one on the right has 1, 2, 3. So we're comparing 2 products, one that is di-substituted, one that is tri-substituted. They both can form. We're not limited to just one or the other. But remember what we talked about with the degree of substitution. The higher the degree of substitution, the more stable it is. The lower, the less stable. And typically when a reaction is going to happen, you want to form the most stable intermediate, the most stable product. And so when comparing the 2 products that are going to form, the one that is more stable is hopefully now logically the major product. So this will be major because it's more stable. This is minor because it's less stable. And who came up with this idea of recognizing stability? Mr. Zaitsev, which is why it's called Zaitsev's rule. So I don't want you to just memorize why this is the Zaitsev product, I want you to understand. Zaitsev's rule says we're going to have the most substituted, and yes, sub is just because I don't feel like writing out the word substituted a million times today. So this is my shortcut for it. Tri-sub means tri-substituted. The major product is the more stable pi bond, is the more substituted pi bond. That is Zaitsev's rule. Question here. Substitution means how many R groups are attached, not to the functional group necessarily, because we could have functional groups on the molecule. In this case, I'm looking specifically at the pi bond. How many R groups are coming out of the pi bond on either side? It doesn't matter which side, you count them all together. And I see a comment here. Zaitsev's rule says beta hydrogen elimination will occur from the less substituted hydrogen or from the more substituted. I'm not sure what you're saying here. It will be the more substituted, more stable product, and that comes from eliminating at the more substituted position. Relatively speaking, since the alkene is the functional group. Yes, in a situation like this, you are absolutely correct. The alkene as the functional group is the most substituted. We're going to stick to elimination reactions today, but if you want to cover any other topic, email me and we can discuss that separately. So now that we understand why we form one over the other, let's take a look at some of the things that happened here. I want you to notice how when we did this reaction, it was one molecule reacting at a time. The starting molecule lost a bromine, a carbocation formed, the base grabbed only a hydrogen, and we got our products in more than one step. So we got a multi-step reaction. That is the idea of the one unimolecular. One molecule reacts at a time. And this right here is the key. When one reacts at a time and we have a carbocation intermediate, that's how we recognize the E1 reaction. So the absolute key, if you walk away with nothing else from today, I want you to know that the carbocation intermediate only happens in E1, not in E2. Because the carbocation is not very stable, it's a slow step. That means that the E1 reaction is a slow reaction compared to E2, which is a fast reaction, just like SN1 was a slow reaction and SN2 was a fast reaction. If your professor asks for the rate of the reaction, it's very simple. The rate of an E1 reaction is equal to some constant K specific to the molecule in question times the concentration of the alkyl halide, the molecule that had the leaving group, meaning the more alkyl halides we have in solution, the faster the rate of the reaction. The less we have in solution, the slower the rate of the reaction, because the more we have, the more that is going to react. With the rate of the reaction, because we're forming a carbocation intermediate, sometimes your professors will ask which of the following will undergo the faster E1 reaction, for example. And let's say you're given something that looks like this with a bromine and something that looks like this with a bromine. What you're looking at here is which of the two is going to form a more stable carbocation that is going to be faster. So let's show each one and see what the intermediates would look like. I get the intermediate when I lose a leaving group to give me a carbocation at the alpha position. So that's my alpha carbon. That's my carbocation. Notice that here I have a tertiary carbocation. Here I have a secondary carbocation. And as we saw in the SN1, SN2 session, the more substituted the carbocation, the more stable it is. And that means this one here will be faster to do an E1 reaction because the carbocation intermediate is so much more stable. If you're with me so far, I want to see smiley faces in the chat. And let's see if we have more questions before we go on. Em, if you remind me, I'll happily do a problem like that after. Sangma, yes, we can definitely do that after as well. There was one more thing I was thinking of that I was going to show you here. I'm trying to remember. Oh, shortcut. Who wants to see a shortcut? Let me see even more smiley faces, and I will show you an awesome shortcut. We'll go back to the same reaction that I started with a bromine here. Let's say your professor gives you the same exact reaction conditions. So you're given H2SO4, H2O, and heat. And your professor says, only draw the major product. No mechanism, no anything else. Just give me the major product. My son says, please. Well, no, he doesn't really say the W. He goes, peas, peas, mommy, peas. So yes, we can definitely do the shortcut. If you only need the major product, and you don't have time to go through the mechanism, and you don't have time to draw out all the pieces, here is what I want you to recognize. I'm going to draw both of the products first. So let me show you a couple of different shortcuts in one. If this is my alpha carbon, and this is a beta carbon, and this is a beta carbon, and this right here is a beta carbon. These are all the blues that I have, so that worked out. I can technically draw what appears to be 3 products. The trick for doing this reaction without the mechanism is first, remove your leaving group, redraw your carbon skeleton exactly as you see it, and you're going to need 1 skeleton for each of your beta carbons that have a hydrogen on it. Then, all you're going to do is draw a pi bond between the alpha and the beta carbon. So for the dark blue beta, a pi bond between alpha beta. For the medium blue beta, a pi bond between alpha and beta. And for the lightest blue, same thing. Now, it looks like I have 3 products, but am I correct? Do I have a total of 3 products here? I don't, because these 2 molecules are exactly the same. If you name them, well, first we have to number it. We have 1, 2, 3, 4, 1, 2, 3, 4. Both of these molecules are 2-methyl 1-butene, because we have a methyl group on carbon 2, and the butene, the pi bond sits between 1 and 2. If these are the same, then we'll just cross out one of them and say we only have 2 products. But I just did the opposite of what I told you I was going to do. I told you I was going to show you a shortcut. We didn't have to draw them both. And here's what I want you to consider. Of the 2 that we have, and let me move this to the top so that I can draw on, whoa, that thing is drunk. There we go, same. Of the 2 that we have, let's start with the highlighter trick. How many groups are coming out of each pi bond? 1, 2, 3, 1, and 2. So we already did this before, and we confirmed that this one here is tri-substituted and this one here is di-substituted. This one is the major product because it's more substituted, more stable. Here's the trick. How can I know without drawing them that this is going to be the more substituted product? Simple. Take a look at your beta carbon. The more substituted your beta carbon, therefore the more substituted your beta hydrogen, the more substituted your product. So this beta carbon here is secondary. This beta carbon here is primary, and this is the same exact thing as primary. If I take a hydrogen from the more substituted beta carbon, I will have a more substituted product. If I take a hydrogen from the less substituted beta carbon, I'm going to have a less substituted product. So without having taken the time to draw any of this, here is what I would have done if I only needed the more substituted product. I redraw my carbon skeleton exactly as I see it, identify my alpha carbon, identify that the most substituted beta carbon is right there, draw that pi bond, and that's it. I didn't waste time on a mechanism, on a carbocation intermediate, and I definitely didn't waste time drawing all 3 if my professor did not ask for all 3, because why draw extra if you don't have that kind of time? Let me know if you like the shortcut. Oh my goodness, what just happened? My laptop is charging, and yet it decided to shut down. So bear with me for a moment. This has happened before, which is why that thing is still on. This thing right here, you know what? While I turn this on, because this is going to take at least a couple of minutes, if you need a bathroom break, go run. You'll come back and will not have missed anything except for Q&A. Let's do some Q&A while I try to get this thing back on. Come on, why does it do that to me? It's charging, but it just decided to die. And it only happens when I'm doing a live stream. I don't know why. Question. Will there be rearrangement if possible to form more stable carbocation? Yes, and I actually have a practice problem prepared to cover just that. So once we get to the extra practice, I will cover that. Also, as a reminder, for the substitution elimination bonus midterm practice worksheet, I couldn't figure out what the name is, so I just gave it all those names. It is elimination reactions, substitution reactions, choosing between reactions, and this is not available on my website. Comment worksheet, and I won't email it to you manually. It's automatically going to send you an email, and you'll get access to it. Okay, my tablet is back. Something went wrong. Yes, I know something went wrong. You turned off on. And it even says it's got a charge. I have no idea what happened. It's so frustrating. Okay. You are the best finger red number. I don't know what that means. Oh, you know what? I think when you put emojis in, it doesn't show and it just types it out. So I assume that was a couple of emojis right there. Okay, another question. Where did it go? Will a carbocation always move? I'm going to cover that because I have a fun trick for you. But first, let me get my tablet back online. Let me know when you see it again. There we go. I appreciate your patience, and it looks like you didn't all run away, so that is excellent. We were talking about the shortcut and finding this faster. So let me know if that was helpful. Well, we did not even get to E2 reactions yet, so let's do that next. The E2 reaction is very similar to E1. In fact, if you remember, where did it go? Right here. If you remember, we opened with the same starting molecule, the same product. The only thing that changed was the reagent. So let's take a look. The E, first of all, has a hidden beta in front of it. And now we already know why it's called beta. The E itself stands for elimination. And the 2 does not tell us the number of steps. It tells us that it is bimolecular, which you should now realize means 2 molecules reacting at the same time, giving me a 1-step reaction. That is not writing. Give me the screen. Here we go. Giving me a 1-step reaction. With the beta elimination for an E2 reaction, we'll start out with the same situation. And in this case, you should already recognize that the carbon holding the bromine, the alpha carbon, is very partially positive because the electron density is being pulled up. That also makes the nearby hydrogens very partially positive. So we'll draw them in 2 different colors. I'm going to show you both products, but I want you to tell me, using the trick from earlier, which one is the major product and why. In this case, I'm choosing to react it with a different reagent, NaOH in H2O. Anytime you see Na, K, Li, these are just positive spectators at the start to show you or to hide the fact that you have a negative reactant. In this case, OH minus is my negative attacker. It is a very strong base. It is so strong and so reactive, it doesn't want to wait for a carbocation to form. Instead, it is going to aggressively reach out for that partially positive hydrogen, grab it off the molecule, and in 1 step, collapses the electrons, which just collapse, kicks out the hydrogen, kicks out the bromine. And in one fell swoop, we have our pi bond. We have our product in one step. Bimolecular, two reacting at the same time in a single step to give us the product. I could have just as easily grabbed the orange hydrogen to collapse the electrons and kick out bromine. That would have given me the product that looks like this. And without looking here, I know that this right here is my major product. And the reason for that is the gray hydrogens are secondary, the orange hydrogens are primary, and primary is more substituted. Primary is less substituted. Secondary is more substituted, making that the more substituted and more stable pi bond. But we have a third product here. We don't have another hydrogen to grab, but what could have happened is the molecule could have twisted and rotated. That means we could have just as easily formed the pi bond looking like this. Di-substituted, mono-substituted. And so this is the minor product, but remember that this one is less stable. Cis is less stable than trans because cis is very close together. Trans is far apart. Close together, far apart. And that makes this one the middle one in terms of stability, where this is the minor product. So just to have a note for you here, trans is more stable. More stable than cis. All right, so I see a comment about antiperiplanar. So let's take a look at what happens specifically. When we have the bromine as our leaving group and the hydrogen as the thing being grabbed. The way this happens, the actual mechanism is the orbitals just kind of collapse. They fall in the direction that they're grabbed. And so when I bring in a base to grab the hydrogen from here, these electrons collapse like that. So they fall like dominoes in one straight path. One falls, collapses into the other, collapses into the other. It cannot change directions. So you have to have everything perfectly lined up. And this is where you'll see the coplanar, periplanar, just different ways of describing it, of perfectly lining them up. Welcome, Connie. I hope randomly is good. I hope you're learning from this. And Cameron, wishing you the absolute best on this tomorrow. Hopefully you will understand exactly what to do on your exam based on this. So let me show you what happens here with a different type of molecule. If I draw this on, I'm trying to think. I have a video where I show this with a Newman projection, but in the interest of time, I'm not going to draw all that out today because I'm noticing the time and there's so many more examples I still want to do. And so what we want to consider here is that the hydrogen and the leaving group do have to be perfectly lined up. And then a couple of keys here, just like we saw for the E1 reaction, no carbocation. Do not ever, ever, ever draw a carbocation for an E2 or an SN2 reaction. The reactant is way too strong, way too fast. There's no time for a carbocation. In fact, this is a fast reaction. So that is another key for the E2 reaction. And the rate for an E2 reaction is equal to some constant K specific to the reaction itself, meaning to the individual molecules. But because it's bimolecular, we have the alkyl halide, the carbon holding the leaving group, and the base, the attacker in question. This right here, 1 and 2, this is where we get that E2, that bimolecular. It comes from the fact that we have two things in the rate equation, where in the E1 reaction, we only had one thing in the rate equation. So now that we've gone through the mechanisms, the rules, all of that, before we jump into practice, as a reminder, To get a copy of today's session notes, as well as the brand new substitution elimination practice midterm worksheet that's not available on my website, just comment worksheet and I'll respond with the link. Even if you're watching the recording, I check the comments and you'll get the link after the fact. Let's go back to the initial example. If I have the same starting molecule and the same product, how can I tell the difference? How can I differentiate between the E1 and E2 reaction? Because your professors will ask. E1 versus E2. There are 4 things that I look at when differentiating between reactions. The first one is the alkyl halide. The alkyl halide, as a reminder, that's the carbon chain. Halide is the halogen, meaning the carbon holding the leaving group. And I want to ask myself 2 questions. Question number 1, can it form a stable carbocation? If I cannot form a carbocation, I immediately rule out E1, because without a carbocation, I can't do an E1 reaction. The key to an E1 reaction is carbocation. And question 2 is not really distinguishing between E1 and E2. It's more about, can I even have an elimination reaction? And that question is, do I have a beta hydrogen? And if yes, which one is more stable? So let me clarify what I mean by do I have a beta hydrogen. If I give you a reaction where I have a CH3Br, and I have you react it with what we've seen already for E2 conditions, NaOH, in H2O, and heat. It looks like I can do an elimination reaction, except I have right there, that's my alpha carbon, but I have no beta carbon. If I have no beta carbon, that means I have no beta hydrogen. I have nothing to eliminate. I have nowhere to put a pi bond. And that means I have no elimination reaction because I have nowhere to put that pi bond. So don't be fooled. Don't let your professor trick you. I've seen many, many students lose points for this. Do not fall for this. Let me just move this over here so I have more room on the page to draw the next one. Do not fall for this. So you will not fall for this, your classmates may. The second thing I look for, especially if I want to differentiate between a 1-type reaction and a 2-type reaction, is the attacker. The attacker meaning the base that is going to carry out the reaction. And I'm looking for one key thing. Is it strong or is it weak? What do I mean by is it strong or is it weak? Sangman, not quite, and I'll show you. A strong attacker is defined by how likely it wants to attack, how unstable it is. What we're looking for is if something is happy, then it is stable. That makes it unreactive or less reactive. And so by definition, it is a weak attacker. It doesn't want to do anything. But if I'm looking at a molecule that is, where did that go? That's the wrong button. Here we go. If I am looking at a molecule that is unhappy, that makes it unstable, and that makes it reactive. What would make a molecule, a measly old collection of atoms, happy or unhappy? Typically, we're looking at one simple thing, and that is charge. Charge is a burden, and molecules do not like that burden. The more charge, the more strong the negative on that molecule, the more it's going to react. And yeah, I can see, and the same principles we looked at with ranking acids and bases, exactly the same thing here. I love that you are referencing that because that means you're tying the topics together. And if you're not sure what Em is talking about in the acid-base session, I teach you how to rank acids and bases. Here, we're looking at the base specifically. And so what I'm looking for is as follows. With an E2 reaction, we'll call this a 2-type, meaning SN2 or E2 is a 2-type reaction. With E2, our base is going to have a charge. So we're looking at a charged base. And that makes it want to attack. It is unhappy. And that makes it very, very strong. A strong attacker is going to give me an E2 reaction. But if I have an E1 reaction, I'm looking at something neutral. And if it's neutral, it's weak. And if it's weak, it's going to be slow because it's kind of happy. And it's not necessarily looking to go out of its way, attacking everything and just causing chaos. So this is what I call a one-type reaction. So let's look back at the starting example. We had H2O. It's weak. It's neutral. It's slow. It waits for that carbocation. But NaOH is really an OH minus. It is strong. It is negative. It is unhappy and aggressive. It will pluck a hydrogen off, kick out the leaving group. It doesn't have any time to waste. It doesn't want to waste time. It wants to react. The last two things that I typically look at don't apply here. Solvent, we're looking at polar product. We already said that. And the leaving group, we want to make sure that it can leave. Another thing I want to show you is what if your professor asks you the reverse? Here is a reaction, and you now have to determine that it was an E1 or it was an E2. So what you want to do is, if you have a reaction condition that looks like this, and you're told H2SO4 with a product given like this, here's what you want to do. In order to know that an E1 reaction or an E2 reaction took place, you want to first recognize that we have a pi bond in the product, right? An elimination reaction gives you a pi bond, and then check the conditions. Are these conditions for E1 or E2? H2SO4 is an acid catalyst. If I have an acid catalyst in solution, I absolutely cannot have a strong base because the acid will immediately neutralize the strong base. That means this had to be an E1 reaction because I couldn't have a strong base. I had to have something weak, something neutral, something like water for solvolysis that gave me this pi bond for the product. But if I changed it up and I gave you the same exact product, and I'm even going to grab the rule with it, but this time I gave you conditions that have NaOH. Step one, identify you have a pi bond in the product. We know that it was elimination because that's how we got a pi bond. And then we identify that we have a strong attacker. The strong attacker, and I don't know why I put the arrow towards the NaOH, the Na portion. It should be the O, whoops, I don't mean to erase that. It should be the OH minus. Na plus is a positive spectator. Strong attacker means that this had to come from an E2 reaction. Why does H2SO4 mean E1? H2SO4 is never by itself. And so that means it had to have water, not given, but implied. Sometimes it's given. In this case, it's implied. And water is weak and neutral. That is why it's E1. It's not the H2SO4. H2SO4 simply tells me I could not have had a pi bond. Now, what if you want to find out the starting molecule? The next step to coming up with a product, with a reactant, is to redraw the skeleton exactly as you see it minus the pi bond. So that means I would have a molecule that looks like this. And then I have an option of putting my leaving group in either position that has the pi bond. So here or here. And the question is which one? Well, I want to consider the fact that Zaitsev's rule means I get the most substituted pi bond. So had I started with a bromine or a chlorine or an iodine here, I would have formed a carbocation, rearrangement, that's fine. Had I started with a bromine right here, same thing. So in this case, it doesn't matter. That means I could have had two starting molecules. So this one or this one with a bromine leaving group here and a bromine leaving group here. Now for the E2, same thing. So I could have had this one or this one because I don't see any difference. So what if instead I had something else? Let's see what I could have done. Say you're given a molecule that looks like this. And you're told that under the reaction conditions of NaOET, which is sodium ethoxide in ethanol, ETOH, you got this product and you have to come up, whoops, that's not what I meant to give you. You got this product and you have to come up with the starting material. The starting molecule, well, first thing we do is identify the fact that there is a pi bond. That means it's from an elimination reaction. We see that Na plus is a positive spectator. ETO minus has a negative charge. It is strong. We know that it was an E2 reaction. E2 reaction does not have a carbocation, no rearrangement. And so I have the option of having drawn my molecule. Well, let's see. I draw both of them and the skeleton for both of them. And then because the pi bond is between this carbon and this carbon, I'll put a bromine here and a bromine here, and then ask myself, could both of these have given me the product? Well, remember the rule from earlier. We have to look at the more substituted beta carbon, which has the more substituted beta hydrogen, and that's the one I would have eliminated. For this one right here, my beta, I only have one option, which means if I put the pi bond here, it lines up with the product. For this one right here, I have a secondary and a primary. That means the pi bond would have gone here. That's not my product. That means this is not my starting molecule. It had to be this one, because if I used this starting molecule and I did an E2 reaction, I would have gotten this as my major product, and that is not what I am given here. So let me know if this helps. Let me know if you have any questions on this. Kamsi says, I was taught this today, but I understand it better now. This makes me so happy because a lot of professors will just rush through and throw information at you. But if you take the time to learn and understand, then you're able to apply what you learn to much more difficult questions. And that is my goal for today. That is what I'm looking for. Let's take a look at, this is the kind of problems that professors love. Without showing the mechanism, because all your professor is asking for is the product, you are given, that one is a methyl group here. Well, that one's achiral, so that doesn't matter. And a bromine here. You're given reaction conditions as follows. H2SO4, CH3OH, and heat. We see that we have H2SO4. That's an H plus. That's the source of H plus in solution and acid catalyst. That immediately tells you acid solution, no strong base. It cannot be an E2 reaction. It would have to be E1. Heat helps stabilize the formation of a pi bond. That's why you see it a lot more in elimination reactions. And then you think, okay, let me do the shortcut that Leah said, which is I redraw my carbon skeleton exactly as I see it. And then I put a pi bond between my alpha and my more substituted beta, which is this one right here. So I would put the pi bond here. That would be incorrect. Remember the mechanism for this. And I don't want you to do this on your exam. I just want to show you the mechanism for this reaction. Forms a carbocation. Here's the thing. This carbocation here is on a secondary carbon. And next to it, I have a tertiary carbon. That means if I move that carbocation, if I do a hydride shift, I will have a much more stable carbocation intermediate. And the more stable carbocation intermediate is preferred. That is the one I'm going to work with. So this is the intermediate. You're not asked to show it though. So what do? Very simple. Here's the rule. Anytime you have a secondary carbocation near a tertiary carbon, you're going to have a carbocation rearrangement. You're going to have a hydride shift. And looking at this molecule, without doing the mechanism, you'll recognize carbocation will form secondary. This right here is tertiary. This is going to be the carbocation position. And then, here's the trick. The new beta is right there at secondary. The new beta is right there at tertiary. Let me show you the beta hydrogen options. You have the green, the dark green here, or the light green here. Isn't this one more substituted and therefore going to give you the major product? And that means the product for this reaction has a pi bond between the carbon that was never the alpha and the carbon that was never the beta because of the carbocation rearrangement. And don't worry, this is a tricky problem. You're not necessarily going to see a lot like this. You're going to see simpler problems. But if you do see this on your exam, you are not going to fall for it. Tori says you made it so easy. I love it. The fact that you understand and now you're finding this easy. This is the hardest topic in Organic Chemistry 1. The hardest reaction in organic chemistry, and you're going to have an easy time with it. I love it. Question. For the first example, there is only one answer. First example. I don't know when you type that, so I don't know. Oh, for this one right here, the answer is both. So in both cases, the answer is both, and that's why I put or. I assume that's where you wrote it. When does the Zaitsev and Hoffman form in E2? So Zaitsev's rule tells us more substituted. Unless you're dealing with a big bulky base, which we're not going to have time for today, then you get the opposite of the Zaitsev product. What if the tertiary carbon and the secondary carbon are separated by a primary carbon? You can't jump 2 positions. You can only ever jump 1. And so if the immediate nearby carbon does not give you a more stable intermediate, it's not going to happen. Let's do another tricky one that professors like to show you. And this goes back to a couple of students asked about the anticoplanar, antiperiplanar earlier. Say I give you a molecule that looks like this. And I have my leaving group over here as an iodine. Next to it, I have a methyl group on a wedge and an ethyl group on dashes. You're asked to react this in a solution of NaOCH3 and CH3OH and heat. So let's analyze what we have here. Na plus is a positive spectator. That means we have a negative here. It's strong. It's negative. I have heat to stabilize the pi bond formation. I have the polar protic solvent, which is the conjugate base of my attacker. This is pointing every which way to an E2 reaction. I have an option of grabbing, let's make them different colors. I have an option of grabbing the green hydrogen or the pink hydrogen. And the question is, which one do I grab? Because from a perspective of substitution, they have the same exact substitution. Each hydrogen is on a tri-substituted, a tertiary carbon. And so the stability of the product would look to be about the same. Let me draw both of them so you see what I'm talking about. Let's actually just make all of this green and all of this blue so that we can just refer to them by that position. At the green position, if I put the pi bond here, then I have the methyl that is no longer on a wedge because it's now on an sp2 carbon. The ethyl is still here on dashes. And if I do it at the blue position, the ethyl is now on an sp2 carbon and the methyl is still on a wedge. So notice everything about them from the way we're looking at it here looks to be the same in terms of stability. Is the answer 2 different products? No. One of them is correct, and one of them is absolutely incorrect. Well, let's see what happens. And the best way to do this is to look at it on a chair. Remember I showed you that the atoms have to perfectly be lined up so I could do a domino effect, knocking off the hydrogen and the leaving group? if I draw this on a chair, and I have my iodine, we'll call this carbon 1, 2, 3. We'll make this 1, 2, and 3. Methyl is up on carbon 1. That makes the hydrogen down. Iodine is up on carbon 2. Let's do that purple. Up on carbon 2. That's my leaving group. And ethyl is down on carbon 3, making the hydrogen up on carbon 3. Which hydrogen will allow me to do a domino effect attack? Only one. I cannot remove a hydrogen from the equatorial position. It has to be axial. Haunted by chairs. Yeah, look at the Budweiser logo. It's really just an organic chemistry drink. It has to be axial, and the iodine, the leaving group, also has to be axial because they have to be lined up so that their electrons can move like dominoes. When I put this axial, so rule number 1, the leaving group must be axial. And then rule number 2, the hydrogen must be axial as well. That means it cannot be this one. It has to be this one. And watch that domino effect happen. If I bring in a base to grab the green hydrogen, electrons collapse up, boom. Perfectly aligned domino orbitals collapsing into each other. That means I grab the hydrogen from the methyl. This right here is my product. This right here cannot happen. And they have to be anti and in the same plane, anti-coplanar. Let me know if this is clear. And if this makes sense, if you understand it, but you don't want to waste time drawing chairs on your exam, let me see hearts in the chat if you want a faster and guaranteed way to get this right without drawing chair conformations on your exam, without wasting time drawing chair conformations. I saw a couple of hearts coming in. So here is something I want to point out to you. Do you see how when I have the hydrogen and the iodine, my beta hydrogen and my leaving group on the alpha carbon in the axial position, do you see how they are trans to each other? Do you see how the green hydrogen is trans to the leaving group and the blue hydrogen is cis to the leaving group, meaning the blue hydrogen is up and iodine is up, but the green hydrogen is down and the iodine is up. So they are trans. Watch this. Without ever having to draw the chair, I recognize that if iodine is on a wedge and it is up, then this right here dashes is down and that is trans. I need to have my leaving group and my hydrogen trans to each other. So I know that it's the green hydrogen I'm taking. I know that it's the green one that I'm going to form a pi bond. Never drew a chair and never had to worry if I had the correct conformation or not. Question. Are the same tricks applicable to pentane rings too, since we can't draw chairs for them? If you are doing an elimination on a pentane ring, then yes, they still have to be opposite to each other. Therefore, the leaving group and the hydrogen still have to be anti. So let me know if you think this trick is going to save you time and sanity and not having to feel like you're being haunted by chairs. So let me know that in the comments. And for even more practice on substitution and elimination and practice choosing between them, is this an SN1, SN2, E1, or E2, make sure you try the practice substitution elimination midterm worksheet. It's not available on my website. Just comment worksheet and I'll respond with the link, even if you're watching the recording. If you're looking for help with more than just this topic in organic chemistry, I'd love for you to come join the Organic Chemistry Study Hall. That is the wrong link. Here's the link. I'd love for you to come join the Organic Chemistry Study Hall, where you'll have access to my entire Orgo 1 video library and Orgo 2 video library. You'll have access to the video step-by-step solution for every quiz that I have on my website. You'll also have access to the step-by-step solutions video for the midterm solving session, which is going to happen very soon. I have it already scheduled out in the study hall, and to my private members-only tutoring and support group where you can post daily study questions so that you're never stuck, you're never overwhelmed, you're never confused. If all that sounds good, I'd love to see you in the study hall, leahforsci.com/join. When I end the live stream, YouTube is going to give me about 5 to 10 minutes in the chat still. So I'm going to end the stream and stay in the chat for a couple of minutes. If you asked a question and I did not respond, go ahead and type it in. I will hang out for a couple of minutes to answer your questions, and then I will see you next week for, are you ready for this? Choosing between SN1, SN2, E1, and E2 reactions without crazy flowcharts. You have to be subscribed to my email to get information on when that happens, because that will not be on YouTube. If you get the worksheet, so if you type worksheet and I email it to you, you'll also be on my notification list for me to send you information for next week. With that, have a wonderful evening, and I will hang out and answer a couple more questions.